an extensibility approach for spatiotemporal stream processing using Microsoft Stream Insight. My name is Jeremiah Miller. In this DemoTrack paper published in Advances in Spatial and Temporal Databases 2011, my co-authors and I present a scenario where a number of mobile devices, such as smartphones, stream their current geographic locations to a server that performs real-time spatial queries on this data stream. The current proliferation of location-enabled mobile devices such as smartphones provides a wealth of opportunities for solutions that leverage spatial queries over these moving point data streams. We implemented two classes of such queries in our demo solution: KNN queries such as find the 3 nearest gas stations, and range queries such as find all the vehicles within a geographic window around mine. Our solution is built on Microsoft Stream Insight, which is a commercial complex event processing engine. We rely on it to handle the temporal complexities of events in the data stream and to process our queries over the data stream. Unlike other products on the market at this time, Stream Insight is extensible by user-defined operators, also known as UDOs, making it an appropriate choice for our solution. We wrote UDOs for performing spatial queries and invoked these UDOs in standing LINQ queries run by the Stream Insight runtime. Our solution architecture involves mobile devices sending their locations over the internet to a server running Stream Insight. We wrote an input adapter that receives the incoming events and provides these to Stream Insight, which in turn runs a standing query on this data stream. The query invokes our spatial query operator, which updates a spatial index and queries that index for the mobile devices that match the spatial query parameters. The results are streamed to the output adapters that display the query results. In the first part of our demonstration, we show the solution working with several smartphones. On the right, you can see the smartphone app that we built that streams its position to the server. The smartphone app also shows its own location on screen, as well as the locations of other devices that matched or did not match the spatial query parameters. On the left is the desktop output adapter, a Silverlight app responsible for controlling the server and displaying the query results. The red place marker is the location of the query phone, which is the phone whose screen is shown on the right side of this video. Blue and orange place markers show the locations of other phones. Orange place markers are those phones that match the spatial query criteria, and blue place markers are the phones that do not match the criteria. The blue phones are only shown for the sake of demonstration. A deployed solution would probably have no need to output the non-matches. As the phones run for a while, we can see their place markers move as they acquire more GPS satellites. This causes the positions of some of the phones to fall inside the query parameters and turn orange. To help illustrate that the UDO is operating correctly, we show a dark gray box around the query phone on the desktop output adapter on the left. This is the outer boundary of the query range. If the solution is working correctly, any device should turn orange if it goes inside the box and blue when it leaves. Now my co-author Miles takes one of the phones out the front door and wanders up and down the street. I take 2 of the other phones out to the alley. As you can see, the phones are now mostly outside the query range. In this part of the demo, we show the solution working with real smartphones and we move them around in space. In part 2 of the demo, we again perform range queries, but this time we use a synthetic dataset. This input stream consists of simulated trajectories of mobile devices and allows us to show the solution working with a larger number of devices with greater mobility. Once again, the query device is shown with a red place marker, and the query matches are shown with orange place markers, while non-matches are shown with blue place markers. The geographic boundary of the range query is shown with a dark gray rectangle centered on the red place marker. As the simulated devices move around the space, their locations are streamed to Microsoft Stream Insight. This runs our standing query that invokes our user-defined operator, which updates and queries our custom spatial index for the phones matching the range criteria, which are then sent by StreamInsight to the desktop visualization output adapter. In part 3, we perform a KNN query with the same synthetic data set. Again, the query device is shown with a red place marker. We've set k equals 5, so the standing query returns the 5 nearest devices, which are shown with orange place markers. The blue place markers are non-matches. As the devices move around, the set constituting the 5 nearest neighbors changes. The new KNN set is picked up by the standing query running on Microsoft StreamInsight and sent to the desktop visualization output adapter seen here. We've shown the solution working with a moving query center as opposed to stationary. The moving query center that we've used in our queries is useful for applications like social networking, mail courier load redistribution, or for routing emergency vehicles. In conclusion, our demonstration is noteworthy because we have used the extensibility framework of Microsoft StreamInsight to perform spatial range queries and KNN queries over streaming geographic data. We demonstrated the solution working with real-time data from smartphones and also with a larger number of moving points from a synthetic data set.